This is number 38 from chapter 6, section 2 in the back of your book. It's a specific heat problem. The specific heat capacity of silver is 0.24 joules per degree Celsius gram. A. Calculate the energy required to raise the temperature of 150.0 grams of silver from 273 Kelvin to 298 Kelvin. Now, I know that I'm making a change in temperature from within the Kelvin scale, but 1 Kelvin is the same thing as 1 degree Celsius, so I can interchange this degree Celsius in my units for specific heat capacity with Kelvin, and it's no issue. So joules per Kelvin gram is the same thing as joules per degree Celsius gram. No big deal, because 1 Kelvin is the same thing as 1 degree Celsius. So with that in mind, I know that the equation I'm going to use is Q equals S for specific heat capacity, M for mass, delta T for change in temperature. Now, I've been given specific heat capacity by the question, I've been given mass by the question, and the change in temperature itself. So all that's left for me to do is plug those values and chug them. Let's just plug those in. So we got 0.24, 150.0, and then 298 minus 273. Alright, so doing a little bit of calculating here. I'm going to end up with 900. Let's see, and that'll be, the unit will be joules there. Let me just see. But the problem is, I have one significant figure represented here. I have two significant figures here, 4, and then 3 and 3. Now here, I don't want to have anything to do past, because it's an addition and subtraction, and I'm doing this first in terms of orders of operations because it's inside a parentheses. I don't want to have any digits past the decimal, because that's the rule with regard to addition and subtraction and significant figures. And then I go to multiply. In here I'll have 2 significant figures. And then I'll multiply by 4 significant figures, then 2 significant figures. So my answer needs to have 2 significant figures. And the way I'm going to represent 900 joules using 2 significant figures is by 9.0 times 10 to the second joules. So in order to take silver, 150 grams of silver, and actually get it to increase its temperature from 273 Kelvin to 298 Kelvin, it requires 900 joules of energy. B. Calculate the energy required to raise the temperature of 1.0 mole of silver by 1.0 degrees Celsius. This is called the molar heat capacity of silver. Alright, so I have the specific heat capacity of silver, and I want to turn this into a per mole issue. Okay, how much energy per mole do I need to pump in to any amount of silver in order to get it to make this temperature change 1 degree Celsius? So I'll start with, let's include the units so we can stay a little clear on that. So I'm going to take the specific heat capacity of silver, which is given to me by the question. And I'm going to multiply that by the molar mass of silver. And you see what will happen here is grams of silver, grams will cancel. So grams are gone. So the units that I have left, I have joules on the numerator. Okay, this gram's gone, so nothing's on this, nothing due to this numerator. And on the bottom, I will have degrees Celsius times moles. This is the unit of what I have left. So what this is saying is, whatever number I come up right here will be an amount of heat energy in order to raise 1 degree Celsius and 1 mole of the substance. So the amount of energy required to raise 1 mole of a substance 1 degree Celsius, that is known as molar heat capacity. And we're calculating it for silver, so we use this 0.24. All that's left to do is pump these numbers into the calculator. 24 times 7.9. Let's see, I have 2 significant figures here, so I'll round this calculator value to 26 joules per mole times degrees Celsius. So in order to take 1 mole of silver and raise that entire mole of silver by 1 degree Celsius, it takes 26 joules of energy. Let's get this set up here. There we go. Alright, C, it takes 1.25 kilojoules of energy to heat a sample of pure silver from 12.0 degrees Celsius to 15.2 degrees Celsius. Calculate the mass of the sample of silver. So we have Q, 1.25 kJ. We have delta T, that is 3.2, right? And then we also have a specific heat capacity of silver given to us by the initial prompt. And so considering the equation, we have Q, we have S, we have delta T. All that's left to do is solve for M, calculate the mass of the sample of silver. So what I will do is I will rearrange this equation algebraically. So I'll have M is equal to Q divided by S delta T. Now it's a simple matter of plugging these values in. So I'll have, let's see. Oh, I don't want to make this mistake. I was just about to write for Q, I was just about to write in 1.25 kilojoules. I was about to pump that in here. But realize when I go to enter in S, the specific heat capacity for silver, I'm going to be pumping in this value, which has a unit joule. Now those bad boys do not play well together. So I'm going to want to change this kilojoules into joules so they'll play nice together. So I'm going to record this as joules. So 1,250 joules. And so I can put 0.24 joules per degree Celsius times mass. And then we'll have 3.2 as the temperature change. Okay, throwing this into the calculator. Divided by 24 times 3.2. Now a calculator is telling me 1,627.6. And let's see, hold on. Let's see, joules are going to cancel. And this is degree Celsius. So degree Celsius is going to cancel. My units after all of this stuff is going to be grams. And I have 4 significant figures, 2 significant figures, 2 significant figures. Alright, so I'm going to use 2 significant figures. That means I have to round all the way out to this 6. So I'll go, best way to do that. I'll just put this in scientific notation, make it a little more simple. So 1, 2, 3, 6 times 10 to the third grams of silver. So if you have 1.6 times 10 to the third grams of silver, or 1,600 grams of silver, and you add 1.25 kJ of heat to that sample, the temperature of that sample will go up by 3.2 degrees.